We're now on to section B. So it says application of your knowledge on nature of roots. The first question we have says prove that the roots of x squared plus 1 minus kx plus k minus 3 equals 0 are real for all values of k. Now, in a question like this, it's very important that you start off by understanding exactly what represents a, b, and c. So a is the coefficient of whatever x squared is. Now, if you look at your term with x squared, there's nothing in front. So your a value is actually 1. Your b value is the coefficient of x. What's in front of x is 1 minus k. And the c value is any terms that do not have x in it. So here our terms without x is k minus 3. Now we start off by writing down the condition. And the condition here is for real roots. For real roots, we know that the discriminant must be greater than or equal to 0. Now, discriminant is b squared minus 4ac. Must be greater than or equal to 0. We're going to substitute in here. So we said that b is the coefficient of x, which is 1 minus k in this case. A is the coefficient of x squared, which is 1. C is the terms that don't have x in it, so it's k minus 3. That is greater than or equal to 0. So we're now going to simplify. And we have 1 minus k all squared. We have a binomial squared, which is going to result in a trinomial. To get the first term, we square the first term. To get the middle term, we multiply both terms together and we times by 2. That's going to be negative 2k. To get the third term, we square the second term. That's going to be plus k squared. Then, negative 4 times 1 is negative 4. We're going to multiply it by k to get negative 4k. Negative 4 times negative 3 is going to be positive 12. Let's gather like terms. We end up with k squared. We've got minus 2k minus 4k, which is minus 6k. We've got 1 plus 12, which gives us 13. And that's greater than or equal to 0. So the question didn't actually ask us to solve for k. But instead, we need to prove that the roots will be real for all values of k. So they will always actually exist. What we can do is, we can change the format of this trinomial from being in standard quadratic format to getting it in the format that we would have after completing the square. So here's what we would have if we complete the square. We would say b over 2 all squared minus 6 over 2 all squared when we substitute. Simplifying, inside the bracket we get negative 3, and once we complete the square we have a positive 9. Now remember, to complete the square, this is an application that you learned in your first term algebra. You write down the first two terms and you add the value. Then you group it, and just want to erase this. Then you group that as a trinomial. Then onto your last term, you subtract the value. So we have the first two terms, add the 9, the last term, subtract the 9. From here, we're going to factorize. And when we factorize, we would have this bracket squared. So when we factorize this trinomial, we're going to have a binomial squared. If you're not sure what to use inside that bracket, remember it comes from your second last step. So our second last step was minus 3. Here we've got 13 minus 3, which gives us 4. And by writing your answer in this format, it shows you that no matter what the value of k is, your roots are always going to be real. Because when you have this bracket squared and you're adding on 4, that will always allow your discriminant to be greater than 0 or equal to 0. And you can see this, for example, if you take k to be 0 here. If you substitute 0, you're going to end up with a value that's bigger than 0. If you substitute 1 as well, if you substitute 1, you'll end up with 0 as your answer. So as you continue substituting values, you see that your discriminant will always be greater than or equal to 0, which means that your roots will always be real. So from here we can conclude and say, therefore, the roots are real. So question 2 here, we're given a graph of f of x, which is equal to negative x squared plus 8x plus 20, that's sketched below. The graph intersects the x-axis at negative 2 and 0 and 10 and 0, and the y-axis at 0 and 20. So those are our x-intercepts and our y-intercept. The point 4 and 36 is the turning point. So everything that they've just mentioned, we can see it on the diagram. Now it says determine the value of k if g of x is equal to 4x plus k is a tangent to this equation of f of x, or this graph of f of x. Now let's just make use of a bit of knowledge from Euclidean. And we know that if we have a tangent line, a tangent is a line that would touch this graph at one distinct point. So if we need the coordinates or the k value here of the one equation, we can work as if we're getting the point of intersection. Since the tangent does touch the graph, they will intersect at a specific point. So to start off, we're going to equate both equations. We can now take everything over to the left-hand side. So when we take everything over and gather like terms, this is what we have. The negative x squared goes over and becomes positive. The 8x goes over, becomes negative. So you have 4x minus 8x, which gives you negative 4x, plus k, and the 20 becomes negative 20. So remember that this section is testing you on roots. And since these two graphs are going to intersect each other once, because that's what a tangent is, it only touches the graph at one distinct point. If we think about that in terms of a discriminant, that should be where the discriminant is equal to 0, since when it's 0, we have one root. So we're going to calculate the discriminant based on this. So I'll continue with the calculation here. Since that space is not enough, we are going to have the discriminant, remember, that is equal to b squared minus 4ac. Let's substitute what we have. Our b value is negative 4. Remember, that is the coefficient of x. Our a value is 1. C is k minus 20. So your c value is whatever constants you have, whatever does not have x in it. Now simplifying here, we have 16 minus 4 times k is minus 4k. Negative 4 times negative 20 is going to be positive 80. Gathering like terms, 16 plus 80 is 96 minus 4k. But remember, there is only one point of intersection between the tangent and the graph. So we only have one point of intersection, which means that the discriminant is equal to 0. So we're now going to take that 96 minus 4k equated to 0. And from here, it's quite simple for us to solve for k. I'll actually take the minus 4k over to the right. It becomes positive. I'll divide throughout by 4, and that gives me k is equal to 24 as my final answer. For 2.2.1, they want, okay, so it says use this graph of f of x to determine the values of p for which this equation will have equal roots. Now remember that for equal roots, our condition is that the discriminant must be equal to 0. So if we get b squared minus 4ac is equal to 0, and we substitute, our b value here is 8. A is negative 1, c is p. Simplifying, we have 64 plus 4p equals 0. Let's keep the 4p on the left. Let's take the 64 over to the right. It becomes negative. We'll divide both sides by 4. Therefore, p is equal to negative 16. So to answer 2.2.2, they've taken the equation, they have equated it to b, and they want the value of b for which the graph will have no real roots. So if we go back to our graph and have a look at it, we notice that at the moment there are 2 roots on the graph because it cuts the x-axis twice. However, there can be no roots if this graph is shifted down. But if the graph had to be shifted down 36 units, the turning point itself would lie on the straight line. But that's not what we want. We want there to be no roots at all, which means that this graph should be shifted further than 36 units. Anything bigger than 36 units downwards will cause this graph to lie underneath the x-axis, and there'll be no roots. So our answer for 2.2.2, b should be greater than 36. And the last one, they've replaced c here. They've replaced actually our constant with m. And they want to know for which values will m have 2 positive roots. So when we talk about positive roots, basically for this graph, we want to know how low can we move the graph downwards vertically. What can, because remember here, m is representing the y-intercept. Remember your format, ax squared plus bx plus c. C is now m, where the graph cuts the y-axis. And we want to know what value or values should m be so that the graph has 2 positive roots. And if we look at the graph, currently our m value is 20. That's our y-intercept. But say that we choose 0. If we choose 0 to be our new y-intercept, and remember 0 is considered a positive value in maths. So if it had to cut the y-axis at 0, as well as whatever this point is, those are 2 positive roots, so that satisfies the condition. Our turning point here would now be 4 and 16. How we know it's 16 is because if you look at the difference between 20 and 36, 36 is 16 units above. So if your y value for your y-intercept is now 0, your turning point, which should still be 16 units above, which would be 16. Another way that we can also get 2 positive roots is if the turning point itself lies on the x-axis. In that case, what would this y-intercept now be? This y-intercept would be negative 16. How do we know that? The turning point would now be 4 and 0, since it lies on the x-axis. And remember, between your y-intercept and your turning point, they are 16 units apart. So whatever m is, m can actually be any value between 0 and negative 16. So if we go back up to that, m can lie between negative 16 and 0. So that is what we will actually have as our m values.